In this topic, we're going to look at the spanning tree protocol operation. Switches use bridging protocol datagram units, or BPDUs, to exchange spanning tree protocol information. A switch will send a BPDU on a port using its own source MAC address as the source address, and it will use the spanning tree multicast address as the destination address. There are three types of BPDUs. There are configuration BPDUs, topology change notification BPDUs, and topology change acknowledgement BPDUs. In the lower left example, we see a topology change, and the switch that notices the topology change is going to send a topology change notification upstream to its designated switch. That designated switch will respond with a topology change acknowledgement, and it will then forward a topology change notification upstream to its designated bridge, which will send a topology change announcement back down to it. Once the root bridge is aware that there has been a topology change, it will send out a configuration BPDU with the topology change bit set. That topology change BPDU will be forwarded to the entire topology so that the entire topology knows about the change. Now, how do we elect the root bridge? It is elected based on the lowest bridge ID, and the bridge ID consists of a bridge priority and the MAC address. The bridge priority will be a number that ranges from 0 to 65,535, and when we look at that with a show command, we're actually going to see that bridge priority and the VLAN number added to it. Now, our default bridge priority is 32,768. And if I looked at that for VLAN 1 as an example, I would see my bridge priority in a show output as 32,769 for VLAN 1. Now, that bridge priority is in integrals of 4096. So from 0 to 65,535, but in increments of 4,096. And of course, the MAC address is unique for every device. So if we have a tie in our bridge priority, the device with the lowest MAC address would be elected the root bridge. Now, once we have the root bridge elected, our other switches are going to designate a root port. And the root port is simply the port on that switch that has the lowest cost to the root bridge. So in our example for switch 1, if I add the cost between switch 1 and switch 3 of 100, and then switch 3 to the root bridge of 100, that would be a total cost of 200. But between switch 1 and the root bridge is just a cost of 100. Our root port on switch 1 will be 100. Now on switch 3, we've got the 200 going through switch 1, but we only have a cost of 100 going to switch 2 directly. The problem is I have two ports connected to switch 2 with the same cost of 100. In the event of a tie here, I can only have one root port, even though I have two ports with the same cost. So switch 2 is sending a port ID with its BPDUs. That port ID for Ethernet 01 is 128.2, and for Ethernet 03 is 128.4. The lowest port ID becomes the tiebreaker, so on switch 3, Ethernet 01 will become our root port. Now, in addition to root ports, which are the port that is closest to the root bridge by cost, we also have designated or non-designated ports. So the root port has been elected on each of these switches. Now we look at all of our segments that are not close to the root. Between switch 1 and switch 3, Ethernet 01 on switch 1 and Ethernet 03 on switch 3, we have the same segment. To determine which interface would be used to forward frames onto that segment, we go back to our bridge ID. Switch 1 with a MAC address of AABBCC004600 has a lower bridge ID than switch 3 where the last part of the MAC address is 5000. Because switch 1 has a lower bridge ID, it will be designated on that segment, and switch 3's Ethernet 03 on that segment will be non-designated. Because the two ports between switch 3 and the root switch, one of them became the root port, the other port, Ethernet 02, will be non-designated. Now, talking about these port states, there are 5 possible port states: disabled, blocking, listening, learning, and forwarding. And all of these port states will have different ways that they handle receiving or sending BPDUs. Will it learn MAC addresses? And then ultimately, will it forward data packets? Now, a port that is disabled is administratively shut down, and it will do nothing. So it will not receive or send BPDUs, learn MAC addresses, or forward data packets. But a port that is in a blocking state, that means that it is an enabled port, but it's not going to be doing full function. In a blocking state, the only STP function that it's going to have is receiving BPDUs. It will not send them, it will not learn MAC addresses, and it's not going to forward any data packets, but it will receive BPDUs so that if there is a topology change, it can learn about it. Now, when a port transitions to listening, it needs to let the network know what it knows. So in addition to receiving BPDUs, it will also send BPDUs, but it's still not going to learn MAC addresses or forward data packets. But when it transitions from listening to learning, now in addition to sending and receiving BPDUs, it is going to learn MAC addresses, even though it's not forwarding packets at that point. But then transitioning to the forwarding state, that is a fully functioning interface, and it will not only send and receive BPDUs and learn MAC addresses, but now it will forward data packets.